Good day and welcome back for part 3 of our discussion on inverse functions. In the previous few videos, we've reminded ourselves of how we define an inverse function, and we've worked through several examples. And in this video, we will remind ourselves what it means for a function to be differentiable, a few key properties in terms of the interpretation of the derivative, and then introduce a formula for differentiating an inverse function at a point and begin applying it to examples. So the reminder is that if a function is one-to-one, i.e. graphically it passes a horizontal line test, then its inverse function is defined so that it undoes the function f. And to begin our discussion of the derivative, I really want to bring us back to the basics. Anytime we develop a new differentiation formula, that really relies upon us going back to how we originally defined what it means for a function to have a derivative. And in Calculus 1, we spend significant time dealing with the definition of the derivative. That is the limit as h approaches 0 of this difference quotient, f of x plus h minus f of x over h. But the observation I want to make is that even though working with this definition of the derivative can seem tedious for specific examples, which it most certainly is, it does, on the other hand, allow us to come up with interpretations of the derivative. And let me just remind you of the two key interpretations of the derivative. The derivative represents an instantaneous rate of change. For example, the derivative of a distance function gives you velocity. The derivative of the size of a population tells you how quickly that population will be increasing or decreasing. The second interpretation of the derivative is that it's the slope of a tangent line at a point. More specifically, the derivative to the curve y equals f of x at x equals a is the slope of the tangent line to that curve at the point a comma f of a. A common question that we asked you in Calculus 1, and we will continue asking you all the way through your Calculus 3 experience, is for a given function, find the equation of a tangent line at a specific value of x or a specific specified point on the curve. So graphically, we can think if we have y equals f of x, and for a specific input a, we have a point on our curve, a comma f of a. And the tangent line to the curve at this point, the one that just hits the curve at that point when you're close to a, has slope given by f prime of a. That is to say, the equation of the tangent line can be conveniently expressed as y equals f prime a x minus a plus f of a. So the point slope form of a line passing through the point a comma f of a with slope f prime of a. So let's now return to this idea of inverse functions. And a question we might ask is, if we know a function has an inverse and it's differentiable, can we find the derivative of the inverse function? And it turns out that in general, finding the derivative of an inverse function can itself be quite difficult, because many times it's difficult to find the inverse function itself. But it turns out that what we can write down a nice convenient formula for is the derivative of the inverse function at a specific value a. And the formula that we have is the derivative of f inverse at a is 1 over f prime of f inverse of a. So as long as we can find the derivative of f and this single value f inverse of a, we can calculate this derivative. And you can see why there's this kind of added hypotheses in there suggesting that we don't want to divide by 0. So let's go ahead and look at a common example illustrating this property. So the questions we can now expect are, for some given function, can we find the derivative of the inverse at some point? And I always start these off in the exact same way. I simply write down what the formula tells us. So f inverse prime of 3 is 1 over f prime f inverse of 3. And this is indicating to us that we need to find two different things. We need to find the derivative of f and the inverse of f at 3. So let's go ahead and start off with the derivative. So the function f of x is 3 plus x squared plus the tangent of pi over 2x. The derivative then, working term by term, would be 0. And you don't have to write that, but just so we can see the derivative of each term being illustrated, plus by the power rule 2x. And I would like you to pause the video for a moment and write down for me the derivative of the tangent of pi over 2x. And hopefully you've done that. And note the tangent of pi over 2x is a composition. So when we differentiate this term in particular, we need the chain rule. The chain rule of differentiation is for differentiating a composition. And just to give the reminder in case we've forgotten how the chain rule works, and I'll put a few reminders down here to the right, the derivative of f of g of x is the derivative of the outside evaluated at the inside times the derivative of the inside. So when it comes to differentiating the tangent of pi over 2x, we differentiate the outside function, and the derivative of tangent is secant squared. We evaluate it at that inside function, pi over 2x, and we multiply it by the derivative of the inside function. So the pi over 2 that we see is the derivative of that inside function, pi over 2 times x. So we now have the derivative. What we need to determine to go along with that derivative is, what is this number, f inverse of 3? And this is very similar to some of the examples that we investigated in our previous video. F inverse of 3 is the quantity that, when substituted into the function f, gives you out 3. So the question becomes 3 plus x squared plus tangent of pi over 2x. Would input of x will give you out 3? And the observation that I would make to help work with this algebraically is, note that we have the desired 3, and if x is 0, the second and third term vanish. So the value of x that satisfies this equation is x is equal to 0. And because f of 0 is 3, f inverse of 3 is 0. So the desired derivative that we are looking for, the derivative of f inverse at 3, is now 1 over f prime of 0. And lucky for us, we've already differentiated f, so now we simply go to that formula for f prime and we substitute in 0. So that would be 1 over 2 times 0 plus secant squared of pi over 2 times 0 times pi over 2. And the real question now becomes, what is secant of 0? So pi over 2 times 0 is 0. And secant of 0 is 1 over cosine of 0. And cosine of 0 is 1. So we end up with 1 over 0 plus 1 times pi over 2. And note the 1 is really squared because it's secant squared of 0, but 1 squared is simply 1. And this leaves us with a 1 over pi over 2. And at a minimum, we should always continue simplifying when we have quantities involving dividing by fractions or functions evaluated at common values. And in this case, dividing by the fraction pi over 2 is multiplying by its reciprocal, 2 over pi. And this gives us the desired solution. Now, let me make the observation in terms of what your work should look like. So throughout the course, I will keep making these observations. How you present and how you write up your work is extremely important. We need to make sure that we are using good mathematical notation. And my analogy is that notation is to mathematics what punctuation is to English. Without using that proper notation connecting our steps, the work that we present is mathematically meaningless. So note what you should include, things like equal signs, and whenever possible we organize our work in a single vertical column. Just like we see here, that makes it as easy as possible for someone to read and follow your work, and we do all of these side computations to the side. And a general recommendation or guideline that I would give you is that you should try to model your work off what we've done in these videos and by looking at the completed class notes. I can hardly complain if you do something the same exact way that I've demonstrated it for you. And hopefully this is something that was, really emphasized when you took Calculus 1. And if not, it will certainly be really emphasized in here, because as the classes get more and more difficult, or even the examples in here get more and more involved, say you have a problem that takes 3/4 or a full page of work, that notation becomes really important to keep your work connected and to hopefully make sure that we're not making silly mistakes. And if you ever have questions in terms of how you should present your work or the mathematical notation involved, do not hesitate to reach out. We will continue this discussion of differentiating inverse functions in our next video. So stay tuned. Take care.